All right, so I want to just get into deductive and inductive reasoning. Basically, it's a process that we're going to have to use to build up to do what's called proofs. Taking what you see and making a conjecture using inductive reasoning, or using facts and definitions, accepted properties, and laws of logic to form a logical argument. So either one of these two are ways of us getting to a conclusion. They're both types of reasoning, like how did I come up to that conclusion? Now, being married, being a man and my wife being a woman, we use different type of reasoning. Men use common sense and women use no sense. Don't tell my wife I said that, okay? I think she would hurt me. Okay, back to this. Deductive reasoning is, again, the idea that I'm using facts. I'm not using some idea, something that's not true. Facts, definitions that are proven, accepted properties, and the laws of logic to form a logical argument. That's deductive reasoning. So it's all based on facts and stuff that's already been proven. Now, inductive reasoning is the process of finding a pattern for specific cases and then writing a conjecture for the general case. So what's a conjecture? A conjecture is an unproven statement that is based on observations. So inductive reasoning says, I'm noticing this, I'm noticing that, I can see this over here. So based on that, yeah, this is it. Like, for example, when I say, I'm noticing you didn't do your homework yesterday, you didn't do your homework today, and you didn't do you may not, I guess I should say, you didn't do your homework yesterday, and you didn't do your homework today. So based on that, you're probably not going to do your homework tomorrow. That's an unproven statement. It hasn't been proven yet. It's not tomorrow yet. But based on my observations, I can make a conjecture using inductive reasoning, which is the idea that I'm looking at patterns and I'm seeing what's happening, and then I make an unproven statement. Now, a counterexample is a specific case for which a conjecture is false. So all you have to do is come up with one counterexample, and then your conjecture is false, meaning your inductive reasoning didn't work out too well. Now, back over here with the deductive reasoning, one of the uses, or one of the things that they use is called the laws of logic. A law of one of them is called law of detachment and the law of syllogism. Detachment says if the hypothesis of a true conditional statement is true, then a conclusion is also true. So we know what a conditional statement is, if and then, okay? And so if the hypothesis is true, then the conclusion is true. All right? Now, the law of syllogism says if the hypothesis P, then a conclusion Q. If these statements are true, it's saying if P then Q, then if Q then R, then P then R. That's basically saying if the hypothesis of a sentence is true and the conclusion is true, and then that conclusion becomes a hypothesis and another conclusion is true, then the original hypothesis and the new conclusion are also true. It's almost like one of the properties, I want to say the associative property of math. When you throw that third one in there, if the first two are true, then the first and the last will also be true when you throw that third one in there. All right. So we got a couple of examples on how to use the law of detachment. All right. Here you go. If two angles have the same measure, then they are congruent. You know that measure of angle A equals the measure of angle B. So let's just focus on that. If two angles have the same measure, then they are congruent. You know that measure of angle A equals the measure of angle B. So how do you make a statement or draw a conclusion using the law of detachment? Because the measure of angle A equals the measure of angle B satisfy the hypothesis of a true conditional statement, then a conclusion is also true. So that A is congruent to measure of angle B. So based on the fact that they have the same measure and they are congruent, then the angles are equal. You can say since they are equal and those other statements are true, then they have to be congruent. That's an understanding that we already have. They're using something very basic to say if two angles are equal, then they're also congruent. But in order to actually say that, we're using the law of detachment to say that if two angles have the same measure, then they're congruent. All right. Another one. Jesse goes to the gym every weekday. Today is Monday. So we're going to use the law of detachment. All right. So it says, first, identify the hypothesis and the conclusion of the first statement. The hypothesis is if it is a weekday, and the conclusion is then Jesse goes to the gym. All right. So they said we got to identify these two first. So they said today is Monday satisfied the hypothesis of the conditional statement, so you can conclude that Jesse will go to the gym today. These are very basic, and I understand that, and I don't mean to make it to where this is really dumbed down, but I'm just trying to get you to understand that these are types of reasoning and logic that it takes for you to be able to look at what we're going to get into and be able to determine the solution that we're going to be looking for. Let's use inductive reasoning. Describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. Of course, I got the answers here, but look at figure 1. You got one not shaded, the other one shaded, split down the middle. Split down the middle again, and 3 unshaded, 1 shaded in the corner. It seems that the shaded one goes in the corner as you look at figure 3 because it's split again, and it's still shaded 1 box in the corner. So what do you think the fourth one is going to look like? It should have a third separation, and in the corner it's going to continue to go there. So it says each rectangle is divided into twice as many equal regions as the figure number. So figure 1, it's got 2. Figure 2, it's got 4. Figure 3, it's got 6. I noticed that each line is dividing each more and more. Sketch the fourth figure by dividing the rectangle into eighths. Shade the section just below the horizontal segment to the left. So this was talking about how each figure, it was divided into 2 spaces. I noticed that it was divided, but I was looking at the number of lines that was actually dividing. Is one right and the other one wrong? No, it's how you look at it. We came to the same conclusion. And so, again, this is all kind of abstract because it's all types of thinking that it takes for you to be able to do what we're going to be getting into. Let's look at one for the law of syllogism, and we'll keep moving, and I want to show you what this is really about. If possible, use the law to write a conditional statement that follows the pair of true statements. Now, I have to tell you, this is not something that we're going to be doing a lot of. This is just kind of getting us in the process of thinking how we're going to be approaching some upcoming problems. If Ron eats lunch today, then he will eat a sandwich. If Ron eats a sandwich, then he will drink a glass of milk. Okay, we're going to use the law of syllogism. All right, here's a solution. The conclusion of the first statement is the hypothesis of the second, so you can write the following. If Ron eats lunch today, then he will drink a glass of milk. That's basically it. That's what this is saying up here. When you look at all this, this first part becomes together with the last part. P, Q, R, then it's just P and R. That's basically the last statement there. All right. If x squared is greater than 36, then x squared is greater than 30. If x is greater than 6, then x squared is greater than 36. So notice the conclusion of the statement is the hypothesis of the first, so you can write the following. Yeah, if x is greater than 6, then x squared is greater than 30. You just put the 2 pieces together. Now, I just want to show you the point of this reasoning stuff real quick. And we're not ready for this, but I just want to talk about it real quick. A logical argument that shows a statement is true. We'll come back to this. All right, I don't want y'all to worry about that right now. Well, yeah, we'll come back to that. Here's an example. They want us to use this diagram to prove that the measure of angle 1 is equal to measure of angle 4. And they tell us that angle 2 is equal to angle 3, and angle AXD is equal to angle AXC. All right, so they want us to prove. So this is a 2-column proof, right? A 2-column proof. Now, you always start off with what is given. So I need to be able to prove that those two angles are true, not just by saying, well, they are. I mean, they're congruent. Well, they start off with the given. And then they say angle AXD is equal to angle 1 plus angle 2. And we know that because the angle addition postulate. Yes, we need to know postulates. And then the measure of angle AXC is angle 3 and angle 4. Basically, we are repeating what they have given us. Started with the given and saying those. And so angle 1 plus angle 2 equals angle 3 plus angle 4. How do we know that? Because the substitution property of equality. If those two are equal to each other, then you can substitute the parts that are equal. And so measure 2 equals angle 3, and we know that because it's given. And then the measure of angle 1 plus the measure of angle 3 equals the measure of angle 3 because we substituted, okay? And then measure of angle 1 equals the measure of angle 4 because of subtraction property of equality. Now, that's a roundabout way given basically what they gave you. But I know that angle 1 is equal to angle 4 because they are vertical angles. I could say that angle 1 is congruent to angle 4, equal to angle 4, because the definition of vertical angles. So you could go this route, or if you see a different route, because I saw that right from the beginning, those two are vertical angles, meaning they're facing each other. But what's the whole point? I'm using some reasoning to go step by step by step by step, statement over here, and then the reason for it. You just can't make up something and it's not true. This is where we're getting to, and that's why I wanted to show you, or showing you these notes on reasoning, because it's laying the foundation of you being able to see or look at a pattern or understand based off some definition where you are going to go or how you're going to prove your statement over here. Now you want to pause this probably and get this down, but this is the some of the stuff that we're going to be using in order for us to lay down the foundation. We have to know postulates and theorems and these things like that. And so you want to get this down. Postulate 5 is really defining what a line is and really defining what points are and non-collinear and a plane. These things are important because they're going to ask us to prove stuff like, is this line in the plane and stuff like that. So you got to know what the postulates are. All right. And so you can go through this. We'll talk about more about this in class. But I just want you to have these in your notes. And then we'll move on to some other things. Yeah, I'm just going through the examples. I don't think I'm going to have enough time to really go through, but I wanted you to have these in your notes. The postulates and diagrams, and really talking about defining items that we're going to be using. The last thing I want to mention, and I mentioned this earlier, is that a lot of times we use some of these properties from algebra. And so I even showed you that on that one proof that we had, that you use these properties from time to time. And so here you have all these properties that we should know, but I want you to have this in your notes again. And they kind of go through how you would solve an equation. And you might want to take a look at this and see, this is the math behind us solving for x. We're using properties every time, and now they're showing you the reason that you do every step. Now, we don't do this, but this is a whole nother side of math that says I'm going to define or prove every step that I take. So there's never a step that I take that I don't have a proof for, and that's the whole idea of proof. This is where we're building up to. One of the more difficult things I have found as a teacher is proofs. Of course, we got distributive property here, and here's another example of the distributive property and how you would use it. But I'm running out of time. These notes are really no assignment for them. These are just laying down the groundwork for us understanding proofs. All right.